Good afternoon, and welcome to the development of fire protection guidance for energy storage systems. Benjamin Ditch is a senior lead research engineer at FM Global and has an MS in fire protection engineering from Worcester Polytechnic Institute in Worcester, Massachusetts. And Thomas Long is the corporate vice president at Exponent and has an extensive fire and flammability research experience with numerous small, intermediate, and large-scale fire and flammability testing protocols and methods.
We're going to talk to you today about sprinkler protection guidance for lithium-ion energy storage systems. And I'm going to give you a little bit of background about why we're talking about this and some history of where we've been and a very brief overview of where we go. And then Ben is going to give you the details into the testing. And so the slide that you're seeing now is data that is provided by the Department of Energy through their Global Energy Storage Database. And this map shows the locations of larger scale lithium-ion battery sites across the globe. And as you can see from the map, the hotspots are in the United States and China. And according to this database, there are over 100 lithium-ion energy storage sites currently across the globe, and there has been about 174% increase in these sites over the last 5 years. So these are gaining a significant portion of the market that are out there. And when we further break that down and we look at some data that is published for the U.S. Storage industry, we can see that in terms of both power capacity and energy capacity, that the lithium-ion chemistry is really the dominant chemistry, making up over 80% of both of those categories. And what's interesting from this data to take note of is the fact that over about the last 10 years, there's been a real exponential growth in the use of the lithium-ion technology and significant growth from where we were in the preceding approximately 10 years, where it was not a significant portion of the marketplace that's out there. And so looking forward, battery applications are a very significantly growing industry. It's expected to be a $90+ billion market over the next 5 or 6 years. And this is really attributed to the fact that the prices in terms of the dollars per kilowatt hour have decreased significantly over the past decade. And so we're all familiar with lithium-ion batteries. They're used in a multitude of electronic products, whether it's in power tools, electric vehicles, other forms of electric transportation, telecommunications, personal mobility. But what we see here in terms of the projections in the global market is that the usage of lithium-ion batteries in energy storage systems is expected to grow significantly over the next 6 years and will be second only to the use of the lithium-ion chemistry in electric vehicles. Now, with all of this comes challenges. The lithium-ion batteries come in different formats. They come in different sizes. They're arranged in different ways. Sometimes they're in modules that are stored on racks. Sometimes they're standalone individual cells, but there's a multitude of different usage for these, and it's further complicated for the where are these used. We are seeing them used in containers that are exterior to buildings. We're seeing them used inside of buildings. We're seeing them in standalone buildings that are dedicated to energy storage systems, in portable containers, in the residential market, and in the commercial market. And so with all of these new placements that are out there, there are new risks. And as these new developments are coming, there's one common theme, and that is that we are seeing more energy stored in smaller spaces. And so as the energy density is up, so are the risks potentially, and we're expecting the energy density to continue to rise as this technology moves into the marketplace. So essentially, with more of this energy in tight places, there's more potential for there to be fire hazards and risks. And currently in the marketplace, authorities having jurisdictions, owners, installers, operators, distributors, manufacturers have been challenged by the past lack of clear direction in terms of what is the appropriate fire protection and suppression strategy for these potential fires. I'm sure many of you are familiar with NFPA 855. It's a soon-to-be standard published by the NFPA on energy storage systems. It just went through a series of NIPMAMs at the World Safety Conference that the NFPA had about 2 weeks ago. And it's got a very broad scope covering everything from indoor and outdoor installations to the separation of these different units, fire suppression, detection, emergency plans. And so this is a document that has gained quite a bit of attention and will be coming out soon. So now a little bit about where have we come from in terms of the projects with the Research Foundation. Many of you are probably aware we did a phase 1 hazard assessment back in 2016 where we looked at lithium-ion battery energy storage systems. And just an overview, this information is available on the Research Foundation's website, but essentially the goal was to develop a hazard assessment on these lithium-ion battery energy storage systems. We conducted a series of full-scale instrumented open-air burns of 100 kilowatt-hour commercial energy storage systems. We tested both an external fire that is trying to attack one of these units, as well as we conducted testings on an internal ignition scenario. And the real focus of this work was to identify the gaps in knowledge and to help us identify where those gaps were, what they were, and what sorts of future research we needed to do. And there were some key takeaways from these tests. The external fire, we got a self-sustaining fire that led to significant thermal runaway. In the internal fire, we did not get thermal runaway outside of where we initiated the fire. But in the external fire exposure scenario, we had significant flaming from outside of the energy storage system cabinet, and we knew from that clearances to nearby combustibles was something that we needed to understand further. We also, in both tests, detected elevated levels of different toxic gases, and that was able to allow us to give some additional guidance to the fire department community in how to respond to these types of fires. And as a result of it, we ended up with about 7 key takeaways in areas for future proposed work. And the work that we're here to talk to you about today is highlighted in red, which was the ideas of how do you suppress these fires and what are the effects of different battery chemistries and sizes on the hazard that can be faced on these different energy storage systems. But there was one common theme that we were able to take away from this, and that was that the fire protection engineering community as a whole, as well as the fire service communities, really needed guidance on these energy storage systems inside of buildings where they could have an effect on the building, on occupants, and general life safety. And that really brought us to phase 2, where we were looking at sprinkler protection guidance for lithium-ion based energy storage systems. Most of the testing went on in 2018. And the real goal here, we were trying to determine what is the appropriate sprinkler protection guidance for lithium-ion energy storage systems in commercial occupancies. Want to thank the Property Insurance Research Group for financially supporting this work, and obviously to FM Global, who graciously conducted all of the testing. But all of these pieces came together with this overriding goal for us to try to develop sprinkler protection recommendations based on real fire data. That was the overriding goal. And so I'm just going to give you a quick thumbnail sketch. Ben is going to give you significant detail on all of this, but we were able, thanks to donations, to test 2 different battery chemistries. There were a variety of small-scale tests conducted to be able to determine that we could induce thermal runaway, and I want to stress that our goal here was to have a fire so that we could understand the best way to suppress it. Those were followed by intermediate scale tests to determine the effect of the system capacity on the overall thermal hazard, which were then followed by large-scale tests, which were broken into two categories, essentially some free burn tests to establish the overall energy storage system hazard, followed by sprinkler tests to determine what type of performance would be necessary to control these fires. And as a result of this work, two reports were generated. There is the Factory Mutual Global test report that has significant detailed information available about the very specific details of the tests, and Ben will tell you where to get that. And then there was the exponent summary report, which was generated as a summary of the overall project, and that is available on the Research Foundation website. And so with that, I will turn it over to Ben to give you all of the details into the tests.
All right. Well, thank you very much, Tom. I appreciate the introduction there, and certainly all the good background on how the world of energy storage has been developing over the last few years. To answer the biggest question you all probably have, yes, we're going to look at videos today. I think that's probably one of the single most important things we can do with this particular hazard is to really show what it is, what these fires look like, and what the other hazards are associated with it. As Tom had mentioned, okay, not hearing any. Okay, so we ran testing starting at the single module level, and based on that, let's see, we had single module, then we went to multiple modules, and then from multiple modules we moved up to full-scale rack storage fires, and that's all done in freeburn. Okay, and that's really to try to assess the impact of scale on our on the fire going from a single module all the way up to a full rack. And then we looked at sprinklered fire tests to take a look at the impact that sprinklers can play on this type of fire. And so that's what that test looked like. And really the main takeaway is that every one of these burned. And this burned in both chemistries. So, but I'm seeing all the comments in the headset. I have my gain turned all the way down, and I have my mic pulled as far away from my face as I can. Maybe I would suggest turning your speaker volume down in this case to drop the volume lower. So this is a surprise. This is just summarizing some of the points that Tom put together. Single module test was really to look at the ignition methodology, making sure that we have a consistent way of causing these a fire, thermal runaway, followed by fire in these modules, and then looking at multiple modules to see development up to full-scale rack testing to really get a full assessment of the hazard of at least a couple of commercial-scale systems. And then following that up with the sprinkler tests, again, to show the effectiveness of protection. To give you a little bit of background on the batteries that we had available, again, we were fortunate here to have a manufacturer that was able to provide enough equipment of two different types of batteries, different chemistries, but enough of each chemistry to run that full gamut of tests. And we were further benefiting by the fact that these were really on the opposite ends of the hazard spectrum. With regard to chemistry, we had lithium iron phosphate on the low end of hazard. Now this tends to be a lower energy dense type of chemistry, but it's also more thermally abuse tolerant, meaning it's less likely to be involved in a fire. On the opposite end, we had the NMC, which is the nickel manganese cobalt oxide battery. Now this is a higher energy dense product, so it's really the direction the industry has been moving, but it also tends to be less abuse tolerant, so it's more likely to be involved in a fire. So I'm providing some discussion here, or some detail here on the capacity of the batteries and on the modules. And we kind of think of this more as a take-home content. That what we want to look at now is if we go down to the full rack description. When you take all these modules and you put them together in series, then the voltage can really add up. So the iron phosphate voltage, if we're fully connected, is around 700 volts, and the NMC is about 1,000 volts. So that's just in terms of electrical safety. When you look at the capacity of the systems, it's important here for me to sort of detail that the iron phosphate system was 83 kilowatt hours, and the NMC was 125 kilowatt hours. So even though these are both, I'm going to show you large-scale results for both of these, it's not 100% apples-to-apples comparison because I'm not testing the same energy capacity. And in the world of lithium-ion batteries, energy capacity is fuel. To have a larger energy capacity, you can have more batteries, you're going to have more electrolyte, you're going to start having an increased fuel load. The other thing I want to comment on is that NFP 855, which is a standard for energy storage systems, now has a 50 kilowatt limitation, where if you exceed that limitation, or if you try to, say, reduce the sprinkler protection requirement or the space separation requirements, then you need to run fire tests. And I think a lot of this work supports that statement because, as you'll see, and consider this as you're seeing videos and some data later on, that these systems are both larger than 50 kilowatt hours. The other thing I want to lay out before we move into some of the test photos and videos is what just a general layout of the racks. So here I have 16 racks, 16 modules within a rack. So there's 2 side-by-side, 8 tiers, and then on top there's the battery management system. Now, I'm assuming that these systems are running under an abuse condition. Okay, so the BMS is not active. There's no active electronic protection for these systems. Because I'm trying to evaluate the hazard of my combustible, we're going to take a reasonable step to ignite the combustible, and then we want to see how the protection system performs. So in this case, the BMS system is essentially just a solid metal box at the top of the rack. In terms of state of charge, we are looking at a use condition, so the modules were at least 95% state of charge for any test. So here I just want to show you what the free burn tests look like for large scale, and then we'll go into the videos to see what the reduction looks like based on sprinkler protection. On the left-hand side, we have LFP, that's the iron phosphate, and on the right-hand side, we have NMC, again, that's the nickel, manganese, cobalt oxide. You might notice I have some timing up here, and that's kind of related to how the test is conducted. And I'll talk about that once we get into one of the videos where I can show you how I did the ignition. But here you can see the fires are kind of face fires, and there's a bit of a difference in perspective of these camera angles. The NMC happens to be a bit closer, but as you see these fires getting large, there is a distinctly larger fire from the NMC. And I'll show you some data to show quite how much of a difference it is here, but it is a very, very distinct larger fire from the NMC. Something else that's unique about the NMC is what happens after you're towards the tail end of the fire. Now, mind you, these are battery fires, and batteries are actually going to thermal runaway, and they're venting an ignitable gas or a flammable gas. So what I've noticed, which was kind of surprising during these tests, is that you'll have all this active flaming coming outside of the energy storage system, and then at some point in time it can just stop. All of the flames just disappear. And you might think that that's extinguishment, but if you look at, particularly with the NMC system, we had what we thought was extinguishment, and then slowly over time, and this can go on for hours, the temperature inside as we're measuring temperatures in there, we continue to increase. Past 1,000 C up to 1,400 C, when you start to fuse your thermocouples, the temperatures continue to rise into this kind of furnace-like combustion. And as that's happening, you can start to see all the metals and stuff inside start to melt, and the energy storage system actually starts to shrink inside there. And that happened for the NMC system. For the iron phosphate system, it didn't really happen. Once the flames are gone, we didn't really see this furnace-like combustion. So there is some potentially differences here that it could be related to the chemistry, maybe related to the materials of construction as well. But there's definitely a difference. Okay, so that is what we saw for the free burn test. And what I want to show you now is a test video. But before I do that, since I can't show you the video at the same time, I just want to just describe a little bit about what you're seeing here, and then we'll go through one of the videos. So this is the NMC sprinkler fire test. And the overheat is going to be of this module here in the bottom corner. And basically all I did was strap 3 heaters to the underside of the module, and then we raise the temperature up at 5 degrees C per minute until we have combustion. There are other ways to do this, and certainly there are more savvy ways to do this. And one of the ones I've seen is people will open up the module and they'll put little small heaters against individual cells, and then they'll cause an ignition, and that'll propagate from one cell to the next within the module. You could also do nail penetrations. You could do overcurrent. So there's a lot of ways you can get to cause a battery to go into thermal runaway. Ultimately, all of these things are just heat. So for simplicity in this test, all we did was strap 3 heaters to the module, and then just let everything else take care of itself. Because of that, this isn't the most efficient way to cause ignition. So that's why you're going to see some long times between when we turn our heaters on and when we have thermal runaway. I'm physically attaching heaters to the cooling portion of the module. So there's some space separation between the batteries and so on, just to consider. The other thing I want to comment is the design of the test. So this is being conducted in our large burn lab, which is about the size of a football field. So it's a very large area. And I do that because I don't know where this energy storage system could be located. And I know that I only have a couple of fire tests. So I want these test results to apply to as many different conditions as possible. And because it's a sprinkler test, sprinklers operate when they get hot. So if you can picture an energy storage system in a storage closet, all of the heat from that fire is going to go right up and be captured at the ceiling level, and the sprinkler is going to operate quickly because it heated up quickly. If you were to put that same energy storage system into a very large room, now you have a lot of dissipation of the ceiling gas flow that's going to allow the sprinklers to heat up slower, and so the fire is going to be larger when the sprinklers operate. And that's a condition I want to have, because once I know I can protect that slow response to the sprinkler, I should be able to apply the results to a smaller room. So you can see here the ignition module is burning now. And again, that's for the NMC, that's done strictly with heat. This type of battery has a tendency to spark as it goes up thermal runaway. So as the flammable gas comes out of the battery, then the sparks will cause ignition. That's the only module that has any form of imposed heating. Any additional fire spread from there is based on the fire occurring in that initial module. And so this can be a bit of a slow process. And there's a sprinkler located just above the top of the array. So the fact that there's a small fire there doesn't really have any implication on the protection because it's not large enough to operate the sprinkler. So if we skip ahead, you can start to see some smoke exiting the rack. Move ahead a little bit farther, and we're 3 minutes into the burning, and the fire is still contained within that first module. So this fire is now going to continue to develop along the face of the array, face of the rack, excuse me, and eventually, what I'll show you in the next video is sprinkler protection. So let's talk about that first. There's really 2 ways you can handle protection for this type of test. The first one would be to try to determine the amount of sprinkler protection you need to provide to adequately protect the hazard. The other way to do it is to look at the level of protection you currently have in the types of facilities where we're seeing energy storage systems. And that's the approach we went with. basically trying to place set what the code is looking at with that 0.3 density. And if you walk into a building and you see an energy storage system and you know there's a 0.3 density, what level of protection are you actually being afforded there? And if that level of protection isn't sufficient, how can you adjust the deployment of the energy storage system so that that protection is actually going to be adequate? And the reason why I went with that approach is these are the only large-scale tests that I'm aware of that are publicly available. So there's not a lot of information for us to fall back on to develop our knowledge of protection effectiveness. And if I were to, for instance, found out that you needed a 1.0 gallon per minute per foot squared density, does that really have a lot of relevance if facilities aren't willing to put that much water in? So we went with the standard 0.3 density with a K5-6 sprinklers, ordinary temperature on normal spacing. So what I'll show you here in a minute is what the sprinkler operation looks like. Before we get into that, I just want to give you a sense of the type of data we're collecting. And I'll show you a little bit of this in this presentation, although to be honest, I don't use a lot of it. That's because the test report is fully available, and there's a lot of data that we collected here. So I'm just going to go to some highlights that will help lead us to conclusions, but there are temperature measurements and all sorts of stuff that are available within the report. In terms of temperatures, we're measuring the temperature of each module, as well as the rack walls. So that's the metal surrounding all the modules. And this is conducted in a large burn lab. So we also have 125 thermocouples at our ceiling and velocity measurements and doing heat flux surrounding the whole storage system. So in total, there's around 300 different instruments measuring during this test. To give you a sense of the density, here's an elevation view schematic of the picture you're seeing. And all these yellow dots represent the location of a thermocouple. So you can see them on each module, and you can see them on the rack walls. So this will really help us understand how heat moves through the module, and also how reliable temperature measurements are within such a densely packed type of hazard. This here is a plan view of the same setup. So the two walls, you can see the W1 wall and W2 wall. Those are surrounding their energy storage system. These would represent, walls in a real facility. And the reason why they're there is first I want to see what the exposure response is. How much heat does this fire push towards those walls? And the other reason is that as fires start to get larger and the radiation from the fire starts to increase, the walls actually present sort of boundary condition where they can re-radiate, they can push that heat back to the energy storage system, and that's another form of heating that can help speed up the fire development. I want to make sure that I am catching that effect. Now in this picture, all these green squares with the Q double prime, those are locations of heat flux measurements. And the reason why I make these measurements is really two goals in sprinkler protection. The first one is, to control or suppress the fire. That means to take the amount of energy the fire is producing, you need to make sure it doesn't get any worse, or try to actively reduce that amount of energy. The other thing you can do is protect the surroundings. So that's why we have such a high density of these heat flux gauges at different locations. And the manner that we did this allows me to then adjust my measurement. So say I make a measurement where the heat flux gauge is 10 feet away, but I'm interested in what would the heat flux have been 3 feet away. With the way we've made these measurements, I'm actually able to make that adjustment and come up with some reasonable estimates. So now moving forward, if we can pull the video down, please. Okay, so now we can see that the fire is developing. It's covering about half of the ignition rack. And you can see some sparkling. You can see some bright spots in the upper portion of the rack as well. So again, this is a bit of a slow development. These modules weigh about 160 pounds each. There's 16 of them, so this represents a very large thermal mass. So the spread of heat through this rack it can be somewhat slow because you have to heat all that mass up. But you can see the increased smoke production. And as this develops, now you can see a large jump in the fire. I think what happens there is that you've heated up a lot of batteries, and now you have sort of a mass thermal runaway event of a lot of batteries, and then you see a large increase in fire size, and that's that first sprinkler operation. So all the additional heat just got pushed up to the ceiling. And now as you watch this, I think it's interesting to consider, what do you think should happen? What do you think this level of protection, what is the sprinkler system actually going to do to this fire? Is it going to control it? Is it going to suppress it? And in fact, what do those statements even mean? You know, if you consider that this energy storage system is inside a metal box, and so the only part open is the face, and the modules are spaced about 1/4 inch apart. So there's no real effective way for the sprinkler to put water inside this rack, and that would be necessary to suppress the fire. So the next thing it can do is control the fire, which means in this case, don't allow the fire to spread any further. So if you watch that target rack now, will the fire spread from what's burning now and then jump to that target rack and then generate a larger fire? And as you can see here, and this will sort of be a theme going forward, the sprinkler protection doesn't really reduce, doesn't suppress the fire, I'll say. But one thing that I was really surprised at is how good of a job it can do at keeping the fire from spreading from one rack to the next. And we'll talk about that more in one of the upcoming slides. I just want to jump ahead a little bit here and show you about 3 minutes after that sprinkler operates. You can see the fire continues burning quite well. We could pull that video away, please. Okay, so before we get into sort of this peak fire size, I want to talk about some of the evaluation parameters. Now there's 3 big ones for this test. The first is the water demand. Certainly a major outcome for any fire test is protection guidance, and part of that is understanding how much water you would need in the protection system. And that's done 2 ways. The first is the number of sprinkler operations. So we would take the number of sprinklers that operate in this test, and you apply a safety factor, and then that's going to be what you typically see in a fire protection code. Water duration is also an important aspect. The energy storage systems are kind of unique in that the fires can last much longer than ordinary combustibles. So we made some additional considerations to make sure that there's enough water for the entire duration of the event. Also looking at the fire spread, particularly does the fire stay within the main rack, or would it spread to a neighbor? And the last one, and this is a very well documented concern for lithium-ion batteries, is the potential for reignition. It's really important here to realize that I'm not trying to actually provide a pass-fail evaluation for these tests. Okay, this is more trying to understand what the hazard is and what type of steps we need to take to bring that hazard down to an acceptable level if that's necessary. So that's really where I'm going to rely on my heat flux data. So how much heat are you pushing from the fire to the room corners or to the walls, to surrounding equipment that you may have nearby, and also the spread of the fire from one rack to the next, which is what we'll be looking at, all the different temperature measurements that we have. So now I'll be showing you the fire when it gets near the peak heat release rate. But before I do that, I want to talk a little bit about these heat flux thresholds. There's 2 different ways you can do this, and the way that we looked at it was a very simplistic approach. And again, this is a broad brushstroke type of analysis to just kind of get a sense for what are safe conditions versus what are unsafe conditions. So the easiest way to do that is to go back to the way we evaluate exposures. And so if you have a combustible object, protection documents such as FM Global's datasheet 1-20 or NFPA's 80A use a value of 12.5 kilowatts per meter squared, meaning that if that much heat is pushed at a combustible object, you can expect it to be involved in the fire. And that's basically a nominal critical value for the ignition of paper or plastic products. And so that's important if you think about how far should an aisle space be between energy storage systems, or what if you have a large trash can, particularly a large plastic trash can, how far away should that be to make sure that fire isn't going to jump to additional combustibles and then spread. The other number that we'll look at is for non-combustibles, and here, again, FM Global's datasheet 1-20 uses the value of 27 kilowatts per meter squared, and that represents the nominal value where you start to see damage to glass or steel. So this could be a sensitive piece of process or expensive piece of process equipment, and it could just as easily be a building column, a structural element of the building that you want to make sure isn't damaged. Okay, now if you don't mind pulling down the video, we'll take a look at this fire once it reaches its maximum. Okay, so now you can see a very large fire developing. We're going to start to see spreading where the fire starts to actually spread horizontally and gets closer to the walls. It also reaches the ceiling and it starts to spread horizontally across the ceiling. Again, I was astounded at this point that we didn't have ignition of our target rack, which, that rack is full of batteries which can go in a thermal runaway due to heating, and you have a fire of this magnitude literally inches away. And so this goes on for a few more minutes. And can we pull the video away, please? Thank you. And that, and there were quite a few people. I'm not sure if anyone on this call was actually witnessing the test with us. There were quite a few witnesses, and kind of one of the we all had the same reaction when this fire was burning and burning and burning, and then boom, the flames just went away. And so we let that sit for about a half an hour, sprinklers on, and then we came in with our water monitors, and because this is the test lab, we had all of our protection equipment set up, and we sprayed water essentially through a fire hose directly at that rack to try to cool it off for quite a while. Once we thought we were in a good spot, we then wanted to see, get rid of all that water from the air and let the smoke spread out and see what was left, see if that fire had in fact extinguished. And if we can pull the video down now, we'll take a look at what we saw. Thank you. And so what we saw was that the temperatures in the rack, we have data to show this, we're actually continuing to, in the target rack, the one on the right, I'm sorry, in the main rack, the one on the right, we're actually still increasing. And you can see this white smoke that's exiting. And in fact, the velocity of that smoke started to increase over time. But what was more concerning was on the left, in our target rack. We saw little sparks going here and there. And given that thermal runaway could be a slow process, this was most likely happening during the initial fire. It's just that there's not a lot of line of sight, so we weren't really able to see it. But eventually, we had a fully developed fire that had a magnitude that was very similar to what the initial fire on the main rack looked like. So this shows that the fire, in fact, can spread for the NMC system, can spread from one rack to the next, but it was significantly delayed. And the importance of that is that if the fire occurred at the same time, so both racks are burning at the same time, then the fire size is going to increase. You could have a fire that's up to, say, double the size. But because it didn't do that, the fire size isn't really ever going to get any larger. The fire duration is going to get a lot larger. And so this has really distinct impact on protection guidance. In one case, you might need a higher level of protection if the fires occur at the same time, whereas in the other case, you just need to provide your water for a longer amount of time. I am noticing a comment whether the target rack fire wasn't related to a short circuit. I certainly just can't discount that. We were forcing an awful lot of water into that rack. Although I do have temperature data of the modules showing that they were elevated at the time. So I think it's probably more likely a combination of the two. But you know, with this style test, it's hard to resolve very, very specific details like that. Hey, can we pull that video away, please? So, now I wanted to show you a little comparison point between the NMC test and the iron phosphate test. Now, I showed you the NMC test because it's a bigger system, it's a more hazardous chemistry, so it makes for, I think, a bit more interesting video. But it is really important to have the counterpoint here to show what other chemistries can do. So here we have on the left the NMC system, and on the right the iron phosphate system. So you can see the NMC system, the fire is up to the ceiling, it's kind of spreading out towards the wall, whereas with the LFP system, the fire is closer, it's not as tall, it's closer to the rack, and it stays much smaller. I'll show you data on this one in a second. Probably a bigger difference is what happens with fire spread. The NMC system, the fire did spread from the main rack to the target rack. In the iron phosphate system, the fire was contained only to that main rack, and in fact this fire only operated one sprinkler, whereas the NMC test operated a sprinkler that had a demand area that would have been over 2,500 square feet, which is kind of a standard number in some of our codes. So there really are differences in the hazard. Now, I do have some data just to really to try to build out a little bit of background as to how we developed, or we're looking at developing protection guidance for these. Now, again, just I think it's important to remember here that the iron phosphate system, which is the two data traces you see right now, was 83 kilowatt hours, and the NMC system is 125. So there is a difference in the amount of available energy between these two systems. So if you look at the dashed orange line, that's the free burn data. And if you look at the solid line, that's the sprinkler test data. So there actually is a reduction in the peak heat release rate from during the sprinkler test. Now, if you compare that to the NMC system, you can see that these two systems do represent very distinct hazards. Now, I aligned these data just to sort of separate everything for easy comparison, but you can see that the NMC data peaks at about 10 megawatts, whereas we're somewhere in the range of 2,000, 2,500 for the iron phosphate system. So these are different hazards. And if we look at the reduction in peak heat release rate, the iron phosphate system was reduced by about 45% by adding sprinklers, and the NMC system reduced by around 34% by adding sprinklers. So these are appreciable reductions. I do think that it's important to ask the question of who cares? 40 or 34% or 45% of a large number is still a large number. So what is the value in that reduction? And the value of that reduction is how this data is used. So the number one way you can reduce the hazard to the surroundings, the simplest way, would be to just move things far enough away so that they aren't exposed to the fire anymore. And if I'm going to do an analysis, I want to do it when the fire is at its peak, as in it's providing its peak exposure to the surroundings. And heat release rate, HRR, by the way, is the heat release rate. That is the amount of energy the fire is releasing. So if I take that peak value, that peak heat release rate number, I can develop this type of graph. So here I'm showing in the vertical axis the heat flux. So this is the amount of energy that's being pushed to my surroundings, and I'm showing that as a function of distance from the fire. And because I have all the different measurements of heat flux, I can actually do this in a fairly confident manner. And so if we look at this, for example, let's look at the NMC free burn data, which is the solid purple lines. Okay, and if you look where it says 3 feet, you can see that the heat flux was somewhere over 100 kilowatts per meter squared. That's a very high number. And if you start to track that farther away, just farther distances away, 4 feet, 5 feet, whatever, you'll eventually start to cross these dashed black lines. Okay, that's the threshold values for non-combustibles. I had that threshold value of 27 kilowatts per meter squared. So once you cross beneath that, therefore we're safe to say that the fire wouldn't damage a non-combustible object. And if we look at combustibles, then you have to keep going, keep going. That's the 12.5 kilowatts per meter squared number, and we have to get out to 13 feet away before we think that combustible objects wouldn't be involved in the fire. So now you can do the same thing looking at the sprinkler data. So if we go for the NMC sprinkler, which is the purple stripe lines, purple and white stripe lines, you can see that you cross the threshold value for non-combustibles around 6 feet, and you cross for combustibles at 9 feet. So the act of adding sprinklers actually means that combustibles could be moved from 13 feet away to 9 feet away. Once you get closer and closer and closer, and that the numbers look better as you go back to the iron phosphate, the LFP systems, because the total peak heat release rate was lower. And so to couple all that together, I could just make a table to make this a little simpler. And what I'm going to show you, what I'm showing you here on the left column is the energy capacity rating. So I conducted tests at multiple scales. My intermediate scale test, which had 6 modules for the iron phosphate, that's 31 kilowatt hours. And then when I go up to that 16 module, the full scale test, that's the 83 kilowatt hours. Now the middle column is going to show you the separation distance. Again, this was just for combustibles. This is that 12.5 kilowatts per meter squared number. This middle column shows you how far away things would have to be when you don't have any sprinkler protection. And when we go to the far right column, it'll show you how far things can be when you have sprinkler protection. Now, I wasn't able to run every test sprinklered, just a large test, and that's why you see that NA for not applicable. And then if you look down, I have the same data for the NMC, and to save everyone the effort of trying to read too much into this table, all of these values exceeded the 3-foot recommendation that you'd see in NFPA 855. Now, mind you, I don't have sprinkler test data for the smaller systems, so we have the information that we have. But I think that this result, at bare minimum, absolutely confirms the need for fire testing. And fire testing around that 50 kilowatt hour criteria that NFPA 855 has in seems to make sense because the larger systems have separation distances that exceed what the code thinks is reasonable. Now, I've heard in the past when I presented on this that sometimes these results can lead people to think that there's no value in sprinkler protection, and I want to make sure I'm being absolutely clear here. There is a very strong value in sprinkler protection, but it's important to understand the role of sprinkler protection here. So, what can sprinklers do? They can reduce the fire severity. We've seen that for 2 different chemistries. They can delay or prevent fire spread from one rack to its neighbor, and they can protect the surroundings. What can't they do? They can't extinguish the fire. You're not putting water directly onto the burning combustibles. You're putting water onto the metal shell around the combustibles. So you don't have a very good transport to get your water to cool those modules. The other thing sprinklers can't do is avoid collateral damage. Certainly there's going to be thermal damage from the fire. There's also going to be non-thermal damage such as smoke and from water damage as well. So there are other protection systems that they can target differently, but sprinklers are going to have that collateral damage associated with it. Now normally what I'd like to do is then show you how to take these results and then just come out with some prescribed guidance. Energy storage systems are trickier than that. And so these are more broad brushstrokes types of guidance and not prescribed protection points. And the reason being is that there's a lot of unknown impacts, and so the three big ones that I can put down here are the impact of battery chemistry, total electrical capacity, and rack design. For instance, iron phosphate might be less reactive than nickel manganese cobalt oxide. But what happens as the energy capacity starts to get larger is an iron phosphate system that's twice the size of an NMC system, more or less of a hazard, and there's no real understanding of how to compare between those right now. And I can actually go down to an even simpler example. The racks that I tested had five-sided metal with a bunch of modules inside. There was no specific metal door on these. And so the fires came out the face, and we saw the fires exit, and we were able to eventually, you could put a fire hose and you could spray water right onto the rack. Well, consider now putting a metal face onto that, a metal door onto that. Now the fire can't get out the face, meaning the heating condition within the rack completely changes. Means you probably have to have some other means of getting hot gas out of the rack, such as a chimney. And if the fire service arrives and they try to hit the energy storage system with a fire hose, they're going to be hitting a metal door. So such a simple change can have a fundamental impact on the hazard and our ability to suppress or fight the fire in the first place, means that there's no real easy way to generalize death. There also needs to be sort of a holistic concept of protection, because now you have fires that could be fairly large inside of a room, so you need to have adequate fire ratings for your ceilings and your walls. I've seen different guidance ranging from 1 hour fire rated to 2 hour fire rated. You also have to realize that these can be very long duration fire events, sometimes exceeding the standard 60 to 90 minute water durations that you'd expect for a lot of our occupancies. And when you do that, particularly if it's an occupied facility, now you have to worry about drainage for all of that water. There are also other hazards that I didn't specifically address in these tests. The first one is cable trays. Especially if you have multiple energy storage systems together, you'll have transmission cables. I've seen a lot of installations where these run above the top of the rack. So maybe that's an obstruction between the sprinklers and the rack. It may also be additional combustible loading. The systems I tested could be 700 to 1,000 volts, so you have a Class C fire there. You also have stranded energy. And these are made of batteries. So even in the event that a breaker's tripped and the energy storage system is now isolated, you haven't gotten rid of the energy within that battery, and so that has implications on fire spread, because as the state of charge of the batteries goes up, so does the reactivity of the battery, and it also has an issue of overhaul, because now you could have a lot of energy left over even after a fire. And the last one is this sort of transition between explosion hazards and fire hazards that batteries can do. I want to address that one with my last video in a couple of slides, so we'll get back to that one. The last one I have on this slide is some comment on fire test requirements. Codes like, or standards like NFPA's 855 say if you want to have a larger energy storage system in a room, or you want to adjust the recommended separation distance or protection, then you need to run a large-scale test. From what I can tell, every energy storage system looks different. In the installations, the way they're deployed, they can all be very different, and they can have huge variations from indoors to outdoors, no doors, doors, one rack next to each other, a bunch of racks next to each other. So they can be very different. And because there's so many installation guidelines, or options, excuse me, it can be very difficult to target the hazard. So all of these tests have to be designed very specifically. And so there's no one-size-fits-all test. And I think it's important to realize there that you could take the same energy storage system that was tested for one type of deployment and have to run a separate fire test on that same system for a different deployment, because you might be looking at a different acceptable exposure hazards or different protection options in place, and that can actually drive you to need to test the same system multiple ways. The last thing here is just a comment on rack configuration. I've seen a few different rack configurations. The first one here would be on the left, is where you have an individual rack surrounded by a metal shell, metal cabinet, and then you have some space separation, and then you have another rack. The next one you could have is where you basically take those racks and you just push them together, but each one has its own same to the individual rack. So you've got metal walls around it. And the third one, which I really hope we don't see, is where you just take a bunch of racks that don't have any metal walls surrounding them, and you just wrap the whole thing in a common skin. And the downside to doing this is that you've taken away the barrier for the heat from the burning combustion in one rack to spread to its neighbor, and so this actually would make fire spread a lot easier. Okay, my last video here is I want to talk about a little bit about the transition between fire hazard and explosions. If we could start the video, please. So, lithium-ion batteries are, I mean, we heard the hazard, the term for the hazard. This is a very sort of uncommon situation where you can have a fire, but if you actually don't have a fire, you eventually turn on the gas. So instead of having a fire hazard, you now have an explosion hazard. And that's a really uncommon transition. And the implication for me as a fire test engineer is that I need to make sure that I'm targeting the hazard that we're interested in. If you want fire protection guidance, you need to have a fire. If you want to have explosion mitigation guidance, then you need to have an explosion. And so this video that I'm showing here is the iron phosphate module. So, and I ran this a bunch of times, and half of the time these gases eventually ignited in a fire. The other half of the time it was substantially delayed, or we never had a fire at all, and we were filling our lab with this flammable gas. So in this case, because this project was designed to develop fire protection guidance, I used a small pilot flame at the front of the module so that as soon as the vent gases came out, they were ignited. And now I can see what happens in the situation when those gases are ignited, and I have confidence in my fire protection requirements. That does not have any relationship now to the explosion hazard, because this scenario can still happen, and so we also have to make sure that appropriate steps are made to mitigate the explosion hazard as well. Can we pull the video, please? So just to summarize here, we conducted small to large-scale free burn tests as well as sprinkled fire tests on two chemistries. And I do think that energy storage systems can be adequately protected, but we need a holistic approach here that couples sprinkler protection along with installation and occupancy considerations. So how far apart the systems need to be separated from each other, and what kind of wall ratings do we need to have, or other environmental systems do we need to have. Also, there's no simple way to extend the tested energy storage systems. There's too many what would seem like minor details, such as adding a metal door or not having a metal door, that can fundamentally change the hazard. And that just means that the large-scale testing is absolutely critical moving forward. And we are, FM Global is now looking to add guidance to our data sheet 5-33. So we're just kicking that off right now. So that'll be coming sometime in the near future. I do want to thank the Property Insurance Research Group and the Fire Protection Research Foundation for their support. I think Tom will have some additional acknowledgments coming up. And this slide here just gives you reference to the different reports available. My full technical report is available at fmglobal.com/research reports. Tom's summary email, summary report can be found at the Foundation website. And I'm working right now on preparing videos, which will eventually be posted on YouTube. And with that, I will hand it back to Tom.
So yeah, thank you, Ben. And so, as Ben highlighted very clearly, our goal in this testing was to look at fire suppression. The main focus was not on explosion, but that's obviously an area that could stand for further work. But as a result of this work, we came up with the following list of potential areas for future work. As Ben highlighted, we could take a look, further into multiple rack installations, evaluating the effects of different thermal barriers installed between the racks. A very important one is the rack design and materials of construction. For example, is there a roof on the rack? Is there a front door on the rack? We could do further work into evaluating the relationship between the various properties of the batteries and/or modules and the fire hazard. Obviously, with the desire, if there is a desire to extinguish the fire, in-rack sprinkler protection is an area that could be evaluated further. And of course, doing varying tests of the demands of the sprinkler system area, water duration, and separation are obvious areas for future work. There were a number of questions that came out of this in terms of after the sprinklers have controlled the fire, what types of hose stream durations and flows are there, and what potential hazards are there for the firefighting community who will be utilizing those hose streams. And of course, there's a myriad of work that could be done at looking at environmental concerns associated with the water runoff as well as the smoke. And so, again, a big thank you to the PIRG, the Property Insurance Research Group, for their sponsorship of this, to Amanda Kimball and all of the staff over at the Fire Protection Research Foundation, as well as the technical panel members who oversaw the project. Of course, to Ben Ditch and FM Global for all of the significant work they did in the testing. NEC Energy Solutions for their donations of the energy storage systems. Retrieve Technologies for helping us dispose of this, and the Exponent team members that contributed to this project.
So, first question I'm seeing here is 50% more energy in the NMC rack, was that considered in equalizing the results? No, it wasn't. It actually took quite a long look at trying to do that. But ultimately, I don't know that there's a direct correlation between energy and hazard, and when you put it with respect to chemistry as well. And since we only have a couple of tests here, and we don't have a lot of different tests of different chemistries or similar chemistries or different energy, it wasn't really possible. The one thing that I can say, and you'll see this in our report, is that it wasn't a linear increase. So one module burning didn't become 4 times larger if there were 4 modules burning. It was actually, as a 3-point line, so you could fit it with a lot of different exponential or polynomial. But the important part is non-linear. So that means that it might not be as simple as just trying to divide by the number of modules. So because there wasn't a lot of data available, we decided to not try doing that now. But I do think that that's a good area of future research. The next one we're seeing is the Fire Waste StatX aerosol fire suppression system effective with fires and battery storage systems. I haven't seen any test data to make any comments. Tom, I don't know if you have anything there.
Yeah, no, I have no data about the effectiveness of that aerosol fire suppression system.
And certainly, when data becomes available, it's something that could be looked at. The next one is the composition of smoke. Is it explosive? I can handle the first part of this. The vent gas, the white gas, yeah, it can be. It's a flammable gas. The electrolyte's flammable, and that is the basis for the white gas. When you see a fire, generally speaking, I would assume that is no longer explosive because you're burning it as it's actively coming out. In terms of the composition, we didn't measure specifically the composition of the gas, except during these tests to evaluate the energy release. So looking at carbon monoxide, carbon dioxide, remaining hydrocarbons, and oxygen level. But Tom, I believe you have some more information on that.
In terms of the composition of the smoke,
Yeah.
there is some data available from the prior work that we've done in this area with the EVs, and that report is available on the Research Foundation website.
Okay, and I know there are a lot of smaller scale tests too, where they'll induce thermal runaway and do, say, FTR analysis to see what the vent gas composition is. One thing to remember here, energy storage systems aren't just batteries. In fact, there's more combustible loading from plastics in these tests than there were from batteries. It's just that the batteries, because it's a gas, that tends to be the part that burns first and develop and can drive the fire, and then the plastics get involved later on. Unfortunately, there's no easy way to separate the fire products from batteries versus fire products from plastics. We tried this extensively in previous testing for lithium-ion batteries and warehouse storage, and really the products look similar enough that you can't differentiate them. And let's see, we see the question, does the report consider the type and amount of off-gas vented? I guess the short answer is no. I'm not quite sure where else this question is going, but we weren't looking specifically at the volume of gas that was released, just at the outcome. To me, the important part is how big is the fire, because that's my exposure scenario. Let's see, next question I'm seeing is the UL 9548 test methods provides gas composition, heat flux, and other data needed by fire protection engineers and AHJs. Does the FM method provide this data? So first of all, FM Global does not have a sort of publicly available test protocol. We have these tests that we've conducted, which in fact align fairly well with what UL 9548 does. One of the bigger differences is that 9548 looks for an implicit result. So you're testing one system and you're determining protection guidance or separation distance or something for that one system. And so that can be a very specific result for that system. And so, for instance, if you want to know is a fire going to spread from one rack to the next, then you would take two racks and you'd separate them however far you want to, and you'd measure the temperature inside that rack where a battery might be, and see what the temperature is, and you can make a real judgment that the fire is going to spread. The testing we did here was, again, a bit of a broader brushstroke to just understand how much heat is being produced by the fire, how much heat is being pushed towards the surroundings, to give us a much better general idea of what's happening. And so we can use this result in a more general way to evaluate different hazard scenarios. It requires, maybe some more heat transfer calculations if you want to know what the temperature would look like inside of a rack. But I think fundamentally the approach with these two test methods are about the same. It's just that we're not looking for a very specific result for one manufacturer. Next question, does the report mention the gas emission when failure, short circuit, or similar situation? No, we don't make any, we haven't done any analysis of that. There is some bench scale testing that will look at that, and certainly it can make a difference, including the temperature at failure, or if you have the pressure at failure can also have some impact as well. That's not something that was evaluated here. Next question, are you sure the target rack fire is heat related and not short circuit related from the water? And we talked about that a little bit during the presentation. And I certainly can't discount that short circuit could have also been an issue. But we have temperature data during the test that shows that some of the modules in the target rack during the NMC test were becoming elevated. So that would lead me to believe that it is at least partly related to the fire, but I certainly couldn't discount that the water intrusion was contributing. Next question, state of charge of the systems was greater than 95% before the test started. We were going for a sort of a worst case use condition. Okay, next question. Does this mean that 13 feet of separation between module trailers is sufficient to prevent a cascading spread of fire? All right, so the 13-foot separation number is specific to the NMC test rack that we tested. FM Global's datasheet 5-33 recommends for an unknown system a separation of 20 feet. And that's sort of a general number when you don't know exactly what you're burning or how much, what's the energy capacity of the system, what does the trailer look like, does it have venting, does it have, when you have all these unknowns in there, a conservative number that we use is 20 feet. Next question, how do you apply the required distance separation and multiple racking? This is a question that comes up quite a bit. When say NFE 855 says an energy storage system greater than 50 kilowatt hours, then you need to have testing. Well, what does that mean, and how far separated things have to be? And so I think that if you have a collection of batteries that exceeds the 50 kilowatt hour, then you need to have separation, or you need to run a fire test to prove that separation isn't needed. There's also a criteria in there that in a fire room has more than 600 kilowatt hours, you should run testing. So probably the simplest way to interpret that would be a single rack should have separation if it exceeds 50 kilowatt hours. That would kind of be in the context of how I ran these tests. And you can see the importance of that, because with the iron phosphate test, the fire didn't spread from one rack to the next, and they were adjacent to each other. But in the NMC test, the fire did spread. And those are the only two data points that I've seen, and you have both sides of the coin on that one. So I think it just drives down the need for more testing. Next question. Have any tests been done where the ESS is in a container and the effect of opening the doors and introducing oxygen or egress of gases? I haven't, we FM Global hasn't done any tests. I know the FAA has a test, and you can find it online, where they were looking at 18650 batteries venting in the simulated cargo hold, and they show an explosion. And this is a condition that I don't think we're going to get away from. If you are venting flammable gas into a room, you can exceed the upper explosive limit in that room, meaning there's too much fuel and not enough oxygen for there to be a fire or an explosion. Once you open up that door, then those values can decrease. The fuel can decrease. You get fresh air in there, and then you could have a fire or explosion. So I think that the condition's real. Tom, maybe you want to handle this next one. Is off-gas detection of any value in early warning? I've heard that HVAC air velocities may affect the readings.
So I don't have any specific data about the HVAC air velocities. Obviously, air velocity could affect any kind of a gas sampling process that was going on. I think that this is something that I'm not familiar with any research out there, but is an area that could be examined as another means of trying to get to an early warning system.
Yeah, I guess the question I would ask is, if you get early gas detection, then what? And that's where the real discussion starts. What effective action are you taking, and what outcome do you get from doing that? So I think that there's potential for value, but that's a discussion that has to be had. Next question. Are you looking at protection suppression methods inside racks, such as water mist or clean agent, etc.? FM Global is not actively conducting any additional tests. That doesn't mean that we may not in the future. And there are a lot of ideas out there. A lot of them, including just discharging sprinkler water inside the racks as well. There's been some other testing. DNVGL did some a few years back, looking at directly applying water onto modules and showing that as an effective means of cooling. They did some tests with foam as well. So there's certainly a lot of work that can be done here. It's just a matter of it being done and it being shared. Next question. Would creating a negative air pressure in a room once gases are detected to deter a thermal runaway? I mean, my initial thought here is no. Thermal runaway itself is essentially when the battery starts to self-heat and the generation rate of heat is faster than the dissipation rate of heat. So the battery temperature just keeps increasing. And I've seen situations where the heat from one battery is sufficient to drive its neighbor into thermal runaway. And when that happens, it can just move all the way through the module. And the batteries themselves are self-contained, and there's no need for fire. So the heating condition of the battery itself can drive the propagation of thermal runaway. In terms of negative pressure, I don't know how that would impact the LEL, the explosive limit of the gas or anything in the room, because there's a lot of questions that would have to happen about how you're doing and what would the impact be. And the last question I see here, is there any data or has there been any testing done on the effect of AFFF high expansion foam? I am not aware of any high expansion foam testing. I know there has been some testing on other types of foams. Tom, are you aware of anything?
I am not, no.
The last question, can you summarize the prescriptive versus performance-related protection requirements in the upcoming NFPA 855? The shortest way to do it would be adequate space separation, and it's a combination of sprinkler protection and space separation. So 0.3 gallon per minute per foot squared sprinkler density, coupled with 3-foot space separation for systems that are less than 50 kilowatt hours. But there's a lot of complexity that goes into understanding that, because not every location is going to have sprinklers or may even need sprinklers or have access to water. So you might just have space separation, in which case that answer can change. It's actually a fairly big document. Okay, so I think this question is, have there been fire tests where the BMS is actively operating? Tom has actually done this, so I'll let him address in 1 second. Before I do that, just the reason why we didn't do the BMS is because, first of all, I want to see an abuse condition. I have combustibles. I want to see what happens when they burn, because if the BMS isn't doing anything actively and my protection system still works, then I have a decoupled solution where my protection is adequate for the hazard, regardless of what the BMS system is doing. For instance, the BMS system could be improper for the energy storage system. It could be set up improperly, or you could have a software issue. So that's some of the reasons why we avoid them. And Tom, do you have anything to add there?
I would just add that in the phase 1 where we did the free burn test, we did test an internal ignition scenario with the BMS running, and we didn't, in that particular unit, did not get thermal runaway outside of the initiating pod within the module that we tested.
On behalf of the National Fire Protection Association, the Fire Protection Research Foundation, Ben, Tom, and myself, thank you for joining us today.